Hey everyone, and welcome to this explainer. Electricity literally powers our entire modern world, but it's completely invisible to the naked eye. Today, we're taking on the challenge of visualizing the unseen by demystifying the specific rules of voltage, electromotive force, and circuit dynamics. It's going to be a fun one.
Okay, let's dive into this. Here is our mental roadmap for how we're going to build our understanding today. First, we'll look at electricity as a water flow. 2. Defining voltage and EMF. 3. Internal resistance and terminals. 4. The direction of current. And 5. Measuring circuit dynamics.
All right, kicking things off with Section 1, electricity as a water flow. Because, honestly, we really need a physical world analogy to grasp these abstract electrical laws. So, here's a question for you. If electricity is totally invisible, how on earth do we confidently map out how it flows? Well, it turns out that even the most seasoned engineers rely on a classic, super intuitive water analogy to picture exactly what is happening inside a solid copper wire.
It's fascinating because the behavior of electricity mirrors fluid dynamics perfectly. Think of voltage as water pressure. It's that driving force pushing the charge forward. Then you've got current, measured in amps, which is the actual flow itself. And resistance, measured in ohms, that's just like the diameter of the pipe. A narrow pipe restricts water flow, right? Well, high electrical resistance does the exact same thing to restrict current.
Moving right along to Section 2, defining voltage and EMF. Now that we've got our physical intuition dialed in, let's transition to the formal physics definitions. Let's start with electromotive force, which we usually just abbreviate as EMF. By formal definition, EMF is the potential energy gained by 1 coulomb of charge as it passes from the negative to the positive terminal of a source. Basically, you can think of EMF as the absolute ideal maximum voltage across a battery. Going back to our fluid analogy for a second, it acts exactly like a water pump, actively giving the electrical charge the potential energy it needs to actually move through the system. But here is an absolutely crucial point you need to remember. Despite the name, EMF is not a physical force. No way. It's actually just a historical misnomer that kind of stuck around. EMF is really a measure of energy per unit charge, which we measure in volts, not a physical push or pull like gravity or friction. At its core, it's fundamentally all about potential energy. Now, what's really interesting about this slide is that comparing them side by side reveals some major differences. EMF is produced inside the electric source, it's constant, and it represents the absolute maximum possible voltage. Standard voltage, on the other hand, is the potential difference between any 2 points in the circuit. It fluctuates. And importantly, the terminal voltage of a battery is literally always slightly less than its ideal EMF. So why is it lesser? Well, that brings us perfectly to Section 3, internal resistance and terminals. Let's see how real-world batteries behave differently than ideal ones. In the real world, batteries just aren't perfect. They have this thing called internal resistance, which we represent with a lowercase r. Some energy is lost just trying to move the charge out of the battery itself, and this creates a voltage drop. As you can see from the formula, the measurable terminal voltage, that's the capital V, equals the ideal EMF, capital E, minus the current multiplied by the internal resistance. And that right there is exactly why a real battery's measurable voltage is always a bit less than its ideal EMF. Okay, jumping into Section 4, the direction of current. There is a really quirky piece of history here regarding which way electricity actually flows through a wire. So here is a super common yet totally fascinating misconception. In reality, actual electrons, the physical charge carriers inside metal wires, they flow from the negative terminal to the positive terminal. But long before electrons were even discovered, early scientists just assumed electricity flowed from positive to negative. We call this older model conventional current. And honestly, here's the wild part. To this very day, electrical engineering universally uses conventional current. That means we literally draw circuit diagrams and calculate formulas as if positive charges are flowing from positive to negative, even though we know for a fact the actual electrons are moving in the exact opposite direction. How crazy is that? Let's move to and see how this builds in Section 5, measuring circuit dynamics. We're going to visualize how all these components actually come together in a real diagram. All right, looking at a foundational circuit, we've got a battery. You can spot the EMF symbol and its positive and negative terminals, and it's connected by zero resistance wires to a resistor. But notice the gap in the loop. That makes it an open circuit. The potential difference, that electrical pressure we talked about, is just sitting there waiting at the terminals. But without a closed path, current absolutely cannot flow. And this brilliantly illustrates what happens next. Close that gap, and boom, we have a closed circuit. Because engineering relies on that conventional current we just talked about, notice how the arrows push out of the positive terminal, travel all the way through the resistor, and then return right back to the negative terminal. Now, if we swap out that simple resistor for a light bulb, it becomes what we call an electrical load. This load is the really crucial component because it does the actual work. It's converting that electric potential energy from the battery into other forms of energy we can actually use in the real world. In this specific case, heat and light. But listen, loop design requires some serious precision. If you add a wire that completely bypasses the electrical load, it creates a short circuit. And since standard wires have virtually zero resistance, this bypass allows a dangerously massive amount of current to flow super rapidly. It converts energy into heat fast enough to melt wires or literally start a fire. So yeah, avoiding short circuits is absolutely paramount when you're designing a system. We have covered a massive amount of ground in this explainer today, from visualizing water pressure in a simple hose to defining the real difference between true EMF and terminal voltage, all the way to mapping out conventional current in closed loops. So I want to leave you with this final provocative thought. How are the invisible forces of EMF, internal resistance, and circuit dynamics working together right this very second to flawlessly power the exact device you are watching this on? It's kind of mind-blowing when you think about it. The next time you flip a light switch or plug in your phone, you'll know exactly the invisible physics happening behind the scenes. Keep exploring, everyone, and thanks so much for learning with me today.